Hello.
Hello, hi everyone. Yes, we'll start in just in 1 minute, Annie, just 1 minute. Thank you all for being here. Okay, thank you all for being here. Welcome everyone to this today's session on a very exciting topic. So we'll be talking about repurposing of electric vehicle batteries as energy storage. Today we'll explore actually how second life batteries can create a more circular battery ecosystem. So we'll look at different aspects, technical, economic, regulatory challenges. So thank you all for being here. It's my pleasure to see that some people are still joining. So before we begin, maybe a few like practical things. First, we are recording this webinar, so I hope you're all okay with that. So the recordings will be sent later to all registered participants, and I've already had a few people asking for those. So if you would like to ask any questions, then you can use the Teams chat at any time. So even during the presentation, but if you would like to verbally ask the question, then please raise your hand during Q&A specific slot. Yes, and for participants also, please keep your mic muted if you're not speaking. Let's start this move forward. So today's session agenda is not very packed, but we hope it will be interesting for you. So we'll have a short introduction into the TREASoURcE project, and also my colleague Noman will will set the scene, so to say, about EV batteries repurposing context. Then we'll look into demonstration sites of TREASoURcE project, and also dive into challenges and policy recommendations regarding this topic. We might have a guest today also from an external guest. Let's see if that works out. From Latvia. And also our core is actually about replicability in Estonia. So we looked into different aspects. How replicable could these practices be in Estonia? And again, my colleague Noman will present insights and conclusions from our work. Okay, yeah, a bit about the speakers. So I am Jelizaveta. I'm organizing this webinar. I'm project manager at TalTech, also a researcher, but EV batteries is not specifically my topic, but I find it still interesting. And Noman is actually here with me, my colleague who is researching energy topics from many different angles, including EV batteries and repurposing the practices. Also from the project, Fride and Aksel are here. Aksel is the one who is dealing actually with our pilots in the TREASoURcE project, and Fride also helping him and researching different results and leading the work package that is focused on this particular pilot. And we hope to have Egija with us maybe later during the webinar. Okay, so let's move forward quickly with a few slides from the TREASoURcE project, and then I will give some word to my colleague. So TREASoURcE project, for some of you who do not know, because I know some people participated in previous webinars. So this is a project about circular economy pilots. The goal is actually to demonstrate several pilots in 3 key value chains: unused plastic waste, reuse of electric car batteries. This is something that we talk about today, and also bio-based waste and side streams. We have the funding from the EU, and the project is of quite long 4-year project. We are, as you see, approaching the end of the project. So we have actually a large consortium from different countries all over Europe. A few partners from Estonia, Norwegian partners, one partner from Germany, then a few research partners also from Denmark. So we quite a lot of people, and of course partners from Finland. Coordinated all by Finnish VTT. So we try to work and find those cooperation possibilities, which is not easy within the big project. Okay, and here maybe to underline again our key value chains: unused plastic waste, batteries, and bio-based waste. But also to emphasize that we focus not only on demonstration, but on the replication too. So our specific objective too is replicated solutions in the Baltics and Poland. So partially that's why we're also here, because we would like to validate some of the criteria of transferability with all of you. And also important is that we try to involve stakeholders, different companies, consumers, communities, experts in the field, while producing and developing our solutions. This is again as a quick summary of basically what has already been said. And stakeholder engagement demonstrations is something that we also find important, and we've already had 2 webinars focusing on those. So yes, please, Noman, are you here?
Yes, I'm here.
Okay, thank you. So please, the floor is yours. You can introduce yourself, and when you need to change the slides, you have to tell me. Okay.
Sure. Okay, so thank you very much, Liz. So my name is Noman, and I'm a research fellow at the Finnish Center for Smart Cities. And today I will talk about this battery repurposing, which is like one of my research areas. So could you please move the next slide? Thank you. So just I will give you some brief introduction. What is battery repurposing and why we need it. So the EV wave is already here. So currently 1 in 5 of the new cars that are sold is an electric vehicle. So in some countries that number could be even higher, but in all over Europe, if you consider this number, it's still a bit lower, but still like 20% of the new cars are electric vehicles. So that's a good sign. But it also means that in the next decade somewhere, there will be millions of EV batteries retiring from the vehicles. And usually when the batteries retire, they just take out the battery bank and they just put a new battery bank in the vehicle, sort of, yeah. So these retired EV packs often retain significant capacity and capability, but it's not usable for the EV anymore. So mostly like it's 70% or 80% of the overall battery storage that was when it was newer. So it still has a significant battery. For example, if it was a 100 kilowatt hour battery, so still it will have 70 kilowatt hours, which is a significant amount for a battery, but not for the car, but it could be used for another, for example, stationary storage demand or renewable integration. It can be integrated inside in the building energy management system. It could be used in a large battery bank for peak shaving, and it could also provide these battery banks some kind of resilience for the energy systems. For example, in case of need that arises from any point, we can still use it. So this second life can help bridge the supply gap while newer cell manufacturer scales. As we all know that the batteries, especially, they require rare earth metal, for example, lithium and some other metals as well. And they are already in a low quantity. And as we all know, the current geopolitical situation, so everybody's trying to get hold of this critical or rare earth minerals. So it's not easy to get the newer battery material quite easily, but we already have the older batteries, so we can use them for different purposes. So it can serve a very good applications for us. So it will also introduce like sustainability and repurposing. Of course, if we are using batteries that have already been manufactured, so it will reduce the CO2 resource saving. These battery banks, if used in a large amount, they could also provide local flexibility services, backup storage for the power system, and of course, the resilience in case of emergency. We can use the electricity from these battery banks. Please, the next slide. So as I was talking earlier, the end of life is not the end of value. Still, the battery contains, as you can see in this graphic, 70 to 80% of the value of the original battery capacity. So it can be used for a second life or some other applications, as we talked earlier. And then in the end, when the battery capacity is significantly lower, then it can be used for recycling purposes. Uh, so typically in an electric vehicle, this automotive life is roughly around 8 to 12 years. It depends on the usage as well, and also the battery charging, discharging circles, how much you charge your battery and how much you discharge your battery. There is a number of fixed cycles here as well. So, but roughly speaking, it's like something between 8 to 12 years. As it's still 70 to 80%, so that's still a significant amount of battery here. Uh, the battery, EV battery, even for a second life, it's still a very large battery. If you buy this capacity, for a newer battery, it will be quite a significant cost as well. Nowadays, these costs are like comparable, but still it's a quite significant cost. Yes, please, the next slide. Okay, so this is the EV battery repurposing cycles or how we use it. So first there is some raw material, then using this raw material, these rare earth metals, we make this battery manufacturing. Then the first life use, it could be, as I said, like average it's 8 year, but it could be 5, 10, 12 years, depend on the car usage or like how you drive your car and how much charging and discharging you're putting in. But still, it retains 70 to 80% of the capacity. So it's not usable for the EV anymore, but it could be used for a second life purpose. For example, residential energy storage, commercial industrial storage, grid balancing, peak shaving, frequency control, all these kind of flexibility services that we call in terms of power system or the market perspective. But still, it can be used for these things as well. The next slide, please. So here are the pros and cons. Comparatively, still it's a little bit lower cost as compared to the newer batteries, but nowadays the cost of the newer batteries are decreasing significantly, so that might not be a very good that not be a very good incentive here, but still in some cases the cost is lower. So then it can be used for energy resilience and backup. So as I explained earlier, for peak shaving, for these other flexibility services, it can be used for quite easily. Then nowadays, especially in Northern Europe, we are having a problem of renewable integration, like excessive renewable integration, if I would say. And in the summertime, sometimes we don't have that much load in the system, so we have to curtail the renewable energy generation. So if we have extra energy generation in the system, we can store it in the batteries, and then we can later use it when the solar panels or the windmills are not producing energy, and we don't have any other renewable energy source available as well. So we can use the energy from the batteries that were stored when the energy generation was excessive. And then, of course, it's good for circular economy and new local value chain. It could also create new business opportunities. For example, there could be different companies, as there are in many countries already, that can be using these EV batteries for repurposing and for different applications as well. But there are some cons as well. For example, still in many countries, the legislation is still a little bit unclear, or it still needs some more clarity from the stakeholders. For example, the battery liability is still unclear. Like, who is responsible for the second life EV batteries? Is it the original manufacturer, or is it the company who is installing this battery? So it still needs a little bit more explanation or like clarity here. Then the lack of harmonized standard. There is not a very significant standards available for the usage of the second life EV batteries. Mostly they are regulated with the EV, with the batteries general standards. Then there is safety and fire risk as well, because in case of any problem, this battery fire is quite different from a usual fire, as it's a chemical fire. So the firefighter need some kind of additional training to put out these kind of chemical fires in case of batteries specifically. Then there are some data and traceability gaps. For example, how this older battery was used, what was its status all over the time when it was used in the first life. So these things are still not available nowadays. The European Union has proposed this battery passports as well. We will talk about these later. So they will improve this data traceability gaps significantly. Then there is also this permit issues and grid connections. In some ways, if we have a second life battery, it still requires some additional testing before it's installed for the second life services, for example, a battery backup or grid flexibility services. So it still requires some additional permits as well. The next slide, please. So this is the repurposing value chain. So the battery, when it's in the end of its EV life, then it's collected by a OEM or a dismantler or a logistic or a storage company. Then in the second step, they perform a diagnostic on the state of health of the battery, its cells probably, and then its data and gradings are like marked. And then it's kind of like, if there is, for example, some cells that are not working, they are replaced with some other working cells. And then the battery is kind of remanufactured uh, with kind of like healthy modules and the battery management system. And then it's enclosed in the container again. And then this battery is deployed for some application at some site. As you can see, this battery storage container, a reference one. So here the key idea is this repurposing succeeds when data plus diagnostic plus safety design are integrated across the full life cycle. So we need the first use history and the second life operation until the end of the life of this EV battery, or even in this EV second life battery here as well. Please, next slide. Okay, so these are some technical pathways. So when the EV battery goes to the end of its life, then it requires some screening. So first of all, some visual checks are there. That is there some insulation or some leakage or corrosion or these kind of like visible faults are there. Then the battery's state of health is estimated, how much capacity is remaining, how much charging, discharging imbalance is there. then grading and matching of the string of the cells. Maybe some cells have aged more, some have aged less. So they try to match their capacities. Then the reconfiguration, electrical architecture, fusing connectors, these are mostly for the safety issues. So they are made sure that they are correct. And the battery management system, it's working properly, and then the thermal management for the battery, that its cooling system is working properly or not. Next slide, please. So here is just an example of a use case that works well. Of course, our next presenters will talk about these pilot sites where some of these use cases have already been installed. So the use case that I'm talking about is the residential community storage that's used for self-consumption and backup for a small scale. So if you have a residential house or a residential building, then you can use these batteries for self-consumption. For example, in the daytime, you can charge it from your solar panels, and in the evening time, you can use it. For the commercial and industrial, it's on a large scale, then it can be used for peak shaving when the demand is very high. Uh, the price could be very higher for electricity, even as we have nowadays 15-minute price. And then PV smoothing as well. When there is excessive PV, then you can store this excessive energy in the batteries rather than curtailing and wasting the energy. Then it can be used for microgrids and critical loads, resilience, island support. For example, these kind of large battery banks can provide resilience in terms of some emergency. You can use energy from these battery banks as well. And then grid edge, congestion relief, for example, if there is excessive PV, that can cause congestion in the system. So usually the system operators use PV curtailment or energy curtailment. So they just lower the PV generation from like 100% to 50% or 30%, and the rest of the energy is just wasted. So that can be used for this congestion relief. Transformer deferral, for example, this congestion can also overload the transformers. So if we have this kind of large battery bank in the system, so that energy will be stored in these battery banks. So the DSOs and the energy companies will be very happy, and they could even pay you extra money for these kind of services. So these are just some of the use cases that can be used, that can be quite helpful if we're using EV batteries. So here are the key takeaways. Repurposing is a system problem. It's not a technical problem anymore. We just need the data, diagnosed safety, and some governance mechanism for the second life EV batteries. Standardization and traceability are key to scaling beyond pilots. So the batteries, second life EV battery standardization and data traceability is paramount important here. So the suggestion is start with a low risk use case and build evidence for bankability. So start with a smaller low scale, and then you can always, of course, scale up if it's economically viable or not. So I think that's all from my side at the moment. Thank you very much.
Yes, thank you very much, Noman. That was a very good, quick look into major topics. I think that we will also cover like during the webinar. So unless I think we don't have like any quick questions, because we would like to go straight into TREASoURcE pilots. So I think that was a very good intro from our side. Now, yes, Aksel, are you here?
I'm here.
Yes. Okay. So thank you very much, first of all, for being here. I know it's a very tough time now, difficult time, project ending and all different other challenges, yes, with deliverables and other things. But yes, thank you again, and yeah, the floor is yours. I will change the slides too.
Yes. So I'm Aksel, and as mentioned, I work at ECOSTOR, which is a Norwegian company working with second life EV batteries in buildings. So we'll talk about these demos and a bit on producing these battery systems. You can take next slide. So some of the technical challenges that was also mentioned by Noman is how to determine accurately the state of health. It's difficult also because the battery management system of the manufacturer is typically restricted, and because each EV battery is different, there are different cell chemistries, different battery management systems, standardization is difficult. And essentially, there's two ways to repurpose a battery. You could either disassemble it, and you can take out some of the cells or modules and test them independently and put them together in a new system. Or you could use the full EV battery pack, which is what ECOSTOR does and what's been done in these demos. So the advantage here is that you can use the original battery management system from the manufacturer. They have already safety functionality, they have measurements of cell voltages and temperatures and so on. It's less work and less material cost, but it also means that if there's one bad cell or one bad module in the whole pack, you cannot really use that battery pack. So you can take the next slide. In our pilot battery system, we have some cooperation with the original manufacturers of these EV batteries. So we both have gotten an estimate on the state of health, and we also have information that makes it possible and to communicate with the manufacturer's BMS. Still, we do a lot of testing and have developed a simple battery tester, which we use. And then the battery system, you can see on the right picture here is a picture of one rack. And each of these racks consists of 2 second life EV batteries. And these racks can be grouped together in a whole system. We have what we developed, which we call a battery interface unit, which is the unit that communicates with the manufacturer's BMS and gets out all the cell voltages, temperature, battery faults, and other data. There's a power converter, which converts from DC power in the battery to AC in the building. We have a smoke and heat detector, safety circuit breakers, and e-stop for some safety measurement. And then we have, when we group together all these racks, we have what we call the master BMS, which takes in all the data from all different batteries and converters, and can basically be given a power set point and use this to sort of balance and distribute the power over the whole system. You can take the next slide, yes. And as Noman also talked about, in order to do anything useful with this battery system, we have these energy services, and it's what we call the energy management system, or EMS, that controls these. In this project, we have done peak shaving and solar support. On the right picture here, you can see from one of the demo sites where it does peak shaving, and the green line there is the consumption of the building with the battery system, while the yellow line is without. And you can also see as the consumption increases, the battery takes over and creates a sort of fixed line around 120 kilowatt, which would have been 140 if the battery system wasn't there. And once the battery system is built, you have to put it somewhere, and as already mentioned, there is fire risk with batteries. So often you need to do some measures here. It's highly dependent on the building, what they have already. Battery fires are also different than normal fires. So typically you have to adapt your ventilation to deal with that. And there may be cost of electrical connections. We typically need to have remote access to it, which has some IT security problems that need to be solved. The temperature should be between 10 and 30 degrees typically for degradation on the battery to not increase, and a power meter to measure the building's consumption. Take next slide. So the pilot sites that was chosen was Trosvik School, which is a primary school in Norway in Fredrikstad, Rudskogen, which is the National Motor Center in Rakkestad, and then in Finland, Lempeletalo, which is a municipality building with libraries and offices and more services. Next slide, please. So Trosvik Elementary School, they have 44 kilowatt solar panels on the roof, and we installed a battery system there, like you can see, with 2 racks, which gives it 80 kilowatt hour capacity and a power capacity of 40 kilowatt, and run peak shaving and solar support. So the battery room here was built actually from scratch in an unused garage. They had to do some work with adapting the ventilation and also electrical connections and access through a 4G router. This system has run for about a year now, and we're not done with the report. So just some early results here is that we had some issues with the battery errors, which we now know was false, but still we needed to troubleshoot it quite carefully, which hurt operation time. The solar production is not that strong, so we have been able to use solar for some days, but it's not that many days throughout the year where we can actually use the battery system for a great benefit here. And also the consumption here is rather flat. So the ideal case for peak shaving is if you have a lot of varying with high tops, which aren't lasting for that long. Yes, you can take next slide. At the Rudskogen, we have a slightly bigger system. Here we just run peak shaving, and it's 120 kilowatt hours capacity and 60 kilowatt power capacity. And here we set the battery system in an outside container, which is great in case you have a battery fire. It's a lot smaller risk when there's not people going there. It's far from other buildings, so there's basically no risk of it to spread. But of course, they needed to put cabling all the way there, internet. They needed to heat this container and keep it in a nice temperature. And because this is a national motorsport arena, they have occasional events where they have a lot more consumption than they have in a normal day, which is perfect for peak shaving. And this has worked pretty well. But also here we had these battery errors, so we had some downtime throughout the running, and this has also run for about 1 year, a bit more than 1 year now. And you can go to the next one. Yes, so at Lemplä in Finland, they also have solar panels on the roof. This battery system used a different EV battery type than Rudskogen and Trosvik, which we have had some more experience with. The capacity was 80 kilowatt hours and power capacity was 40 kilowatt. And then the services, peak shaving and solar support. Here they had the electrical room on street level, which they used for the battery room. They added some aerosol-based fire suppression system in case of battery fire. And they also put this protection device between the battery system and grid, which all of this was quite a bit of cost for them, for the battery room. And here, because this was a EV battery that we had more experience with, we actually haven't had that much operational issues. Unfortunately, the solar panels here, it's not really strong enough to make a big benefit. And also the billing system here is quite different from the one in Norway. So while the peak shaving has worked fairly well, the actual savings on the electrical bill is not as much as in Norway. And you can take the next slide. So what have we learned and what has been the challenges? Of course, there is additional development cost in these second life EV batteries. We've seen that because we have 2 different EV batteries, there is significant extra development cost when you add a new type of EV battery. While we do have some cooperation with the manufacturer, this is still not kind of a complete where we know everything. We still need to do a lot of additional testing and trying to figure out how to to talk with it, how it works, what can cause it to give battery errors, what errors are dangerous, which one are not. And we also saw the installation cost of the battery room. This is sort of non-obvious for the buyers or the customers here. And it can actually be a very big cost, highly dependent on the building. This is also partly due to, like Noman also talked about, there is not that much regulation and experience with this. That's true for batteries in general, but especially for second life. So in all of these pilots, there were hired fire consultants. This cost money, and when there's not like a clear regulation of what you need to do, typically you need to do a bit extra because of the uncertainty, which all takes hours and cost compared to just following a formula of what you actually have to do in a battery room. The operation time has had some issues. This is partly because it's a second life system. It's difficult for us to know which errors are dangerous, which one are not. The greater uncertainty requires greater caution. So in our case, the most typical error we got was we saw a claim from us that there was an installation issue. And of course, it seemed a bit unlikely that more batteries would get these installation issues. So we didn't think it was true. But of course, if it is true, you need to take it seriously. So you have to do a lot of troubleshooting, make sure that this is not the real issue. In the end, we did find the reason for the issue, which was basically sort of a CAN communication misinterpreting issue that happened. This happened maybe once every 3 months, so it's very difficult to troubleshoot. And we did, with the update now in December, fix it, and we haven't seen it since. But of course, it hurt operation time. It was additional cost of troubleshooting and development to fix the problem. And this is also a bit it's a shared responsibility, which is difficult to define. Is it? I mean, the original manufacturers didn't make these EV batteries to be used in second life, but still, we don't know exactly how it works. So who's the responsibility for it to work? It's sort of difficult to define. Yes. So I've been talking about all the issues, but we also have to remember that the pilots have essentially worked. We've shown that they can successfully be worked as energy storage. Of the problems in the project, it's been so far more limited to the EMS, meaning the controlling of the system, the building system that maybe not favor peak shaving so much, and also the building characteristics with the solar power not being really strong enough in the buildings. But these issues would have been there regardless if it was a first life battery or a second life battery. The uptime has been an issue which is probably related to some degree to second life, but this could be more of a startup issue. These are pilots where we have done a lot of learning. Some of them we've already fixed. But yeah, the question is would people want to choose a first life battery instead of a second life? Is there enough incentive to choose the second life? That I think maybe will be talked about a bit later also. So I think that was all from me.
Yes, thank you very much, Aksel. Yeah, that was really interesting also to understand the issues, the problems, the learnings. I think this is why we are all doing it, and why we have this conversation, because otherwise we don't want to talk only about good things. I think we have to learn from something. So it was really, really interesting. Thank you, Aksel. Let's see, we have some questions. They might be for you, but I think Fride or Noman can also take some if needed. So first, what percentage of electric vehicle batteries can be recovered approximately? And the second one, is the quality of recovered batteries categorized? I assume that their condition varies at the time of recovery.
Yeah, I think the first question probably Fride has a better answer from me than me. I don't know if you want to take it, Fride.
Yeah, this is still quite new, so I don't think there's really any good numbers for it. I've seen numbers saying something like 50%, but then again, it's this is still a very new market, so I think it's really difficult to say very accurately how many of the batteries can be reused.
Yeah, I think also it might change with time. We've
Absolutely.
seen for us at least the temperature control of the batteries has gotten better with time. We have NMC batteries, which is typical for second life now, but it might be LFP later, which in theory should last longer and maybe give a better percentage. But yeah, I don't have a number either. That's
But I think just it's worth mentioning also in that regards the LFP batteries. So right now, it's not really economically viable to recycle LFP batteries because you don't have the valuable materials that you have in the NMC batteries. So right now, it's more. I would say it's more feasible to do life extending measures on the LFP batteries than NMC batteries. Because recycling is too expensive, essentially.
Yeah. Okay. And what about the second question about the categorization?
Yeah. So in our case, well, for one of the EV batteries, we had some numbers from the manufacturer. We also did testing ourselves, so they're categorized so that each rack we put together batteries with kind of same aging and same capacity. Otherwise, one would kind of make issues and put down the other one. So yeah, it's true their condition varies at the time of recovery. Also how they're used, how they were stored, but yeah, we test them and put together as similar as possible batteries.
Okay, thank you. Noman, do you want to ask yourself? Maybe.
Yes, I was just curious, like, have you done some sort of like economic analysis for the pilot site, or are you planning to do it? For example, like how much energy costs were saved using these battery banks? Because that will be a really interesting business case, or like it will show these things.
Yeah, we are working with the report now, so we will look in these things. But yeah, I wonder if I should take some early, but we decided not to, sort of, because we're in the middle of it. So was just some early indication, but not any numbers here. But that will be in the final report.
Yeah. Okay. Thank you.
We should also be able to present some of that in the final consortium meeting in Brussels in April.
Okay. Okay, thank you very much, Aksel. I don't know if you can leave, or do you want to leave, or you can stay. So yeah, feel free to go if you need to. Yes. But Fride, yes, the floor is yours. Please.
Yes, thank you, Jelizaveta. So yeah, my name is Fride Vullum-Bruer. I'm a senior research scientist in SINTEF, and I've been working together with the ECOSTOR on this VP4, and we worked a lot on the different aspects of the second life use. So you can just go ahead. So I think a little bit of my presentation is going to be repetition of what's already been said, so I'm not going to spend too much time on all of it, but a little bit of the background, which was also mentioned by Noman, is that we see a huge rise in the market for stationary storage, and also with all the electric vehicles that are now flooding the market. I mean, in Norway, we have almost 100% of new cars sold are electric vehicles. So we have a lot of electric vehicles on the roads. We're more than 700,000 cars now in Norway that are electric. So we see that there's a huge potential for second life batteries to fill this gap. If you can just go to the next one. And of course, what's already been mentioned a little bit as well, but there's with the change in the power system that we see now, with a lot more renewables coming in, there's the flexibility needs. If you look at the figure to the left here, you see that it shows the hour-to-hour flexibility needs per region. This is the blue ones are numbers from 2021, and the green are predicted numbers for 2030. And you can see that all across the world, the flexibility needs are really increasing significantly. And the figure to the right, that shows how those flexibility needs are predicted to be met. The top line, so one is for advanced economies, so Western Europe, the USA, and in the industrialized countries. The others are for more emerging markets and developing economies. And then there's two different scenarios. One's for we have the actual numbers for 2021, and then they have predicted two different scenarios. One, which is a more conservative, which is the STEPS analysis, and the APS is a more forward-thinking scenario with more inclusion of renewables and more storage in the system. And what you can see if you just click one more time. Yeah, so I've just circled the parts that shows the battery, which essentially shows that regardless of the scenario, the batteries will play a pretty significant role in meeting those flexibility needs for the future. So we see that batteries is going to be more and more important, not just for EV market, but also for the stationary market. You can go next. So here, this has been mentioned a bit already, so I'm not going to spend too much time on the slide, but in the EV battery value chain, we have different ways of, we have these sort of 9 R's. I haven't included all the R's here, but we can do a repair, it's a refurbish, it's remanufacture, repurpose, recycle, and recover. We have obviously been focusing on this repurposing part to try to use these batteries for a second life. You can go to the next. So one of the tasks in the TREASoURcE project was to identify challenges and barriers for second life battery use. When we started this work, we started by splitting these into different categories. We looked at the cost of circular strategies. We looked at technical challenges, regulations and legislation, eco-design, and safety and reliability. These were the 4 main areas in addition to cost that we looked into. You can go to the next. So starting with regulations and legislation, which has been mentioned a little bit already, but what we see here is that there's really a lack of regulatory environment, testing, and safety standards for repurposing electric vehicle batteries. Right now, there's a lot of different methods being used. The other challenge is that we know in 2023, the EU battery regulation, in August 2023, it came into action, and there's a lot of different parts of that that's going to be kind of gradually implemented over the next years. What we see is that the regulation favors recycling of materials above lifetime extending activities. So second life is mentioned quite a lot throughout the battery regulation, but there's no specific targets or goals set for repurposing or second life. For recycling, on the other hand, they have set quite strict targets, which I've included some of these in the table at the bottom here, where we see that they have minimum recovered content in new batteries, which is a gradual implementation starting in 2031. And also material recovery targets for waste batteries for these main materials. And as you can see here, LFP batteries with the lithium iron phosphate really don't go in under these different, apart from the lithium, of course. So we think that this could be a real issue in a few years, where batteries will need to be sent to recycling rather than have a second life because they need the materials. Right, you can go to the next. So for the technical challenges, and I think we will still see quite a lot of technical challenges, and a lot of reason for that is that we see that one thing is the historical data stored in the battery. We could see some changes there with the battery passport being implemented, hopefully, but also there's a really large variation in the battery chemistries. The figure to the right here shows how the chemistries have developed and how they're predicting to be developed. So NMC batteries have really dominated the market, but we see that LFP is taken over more and more, and especially in China, much of the new EV being produced for the Chinese market are based on LFP batteries. So this can pose a challenge for different life extending measures. And the batteries, as we know, the technology develops really quickly. So what you have kind of, if you think you've found some way of repurposing one set of batteries now, then in 2 years the batteries can look very different, and you need to change everything. You can go next. There's also technical challenges when it comes to dismantling. So as Aksel just told you, they actually have chosen to reuse the whole battery pack, which kind of avoids a lot of those types of challenges. But there's other challenges that comes also with that. And of course, if you choose to reuse the whole pack, that means if you have one pack with 1 or 2 faulty cells, you have to discard the whole pack. So the number of sort of batteries that you can reuse that way will be lower compared to if you dismantle down to, let's say, modular cell level. But the dismantling part can be quite challenging because a lot of the EV batteries are built in place. So to kind of fit specifically into the car, they use a lot of sort of glues and epoxies and welding to make the battery kind of fit into the car, which makes the dismantling quite challenging. And also diagnosing batteries can be quite challenging because if you have one, or let's say you have 2 similar batteries at the same state of health, it doesn't mean they've degraded the same way. So one battery could then continue to degrade very quickly while the other one can last still for quite a long time. So it's state of health isn't necessarily the one and only way to kind of diagnose a battery because the degradation mechanisms are so complex that it can sometimes be difficult to know the further use. Yeah, thank you. Also, as I mentioned a little bit already, part with eco design, which right now there's no standard set for the EV industry where they can design their batteries any way they want to fit into the vehicle, which means that even the same car model built in the same year, let's say one car that's built in January and another one in October, the batteries can be different, even for the same model car. So the EV manufacturers, they change things all the time, and which makes things a lot more challenging for dismantling. So there's an eco-design directive that's been launched in Europe, which also is valid for the batteries, but I think we still need a lot more stricter regulations on how batteries can be designed in order for them to be easier to dismantle and remove from the vehicle. Can go next. So these are the last 4 that I put into the same slide because they're somewhat related, and it's to do with safety and reliability. We know that lithium-ion batteries used in EVs, they are top of the line quality. They are inherently very safe, but so there's not very often that you see incidents with EV batteries, but if it does happen, it can be quite detrimental because EV battery fires or lithium-ion battery fires are very difficult to extinguish and to control. This can also pose some challenges with public opinion, that people are afraid and they don't want the batteries. They get kind of a bad reputation for being more dangerous. It's also with regards to reliability, which I mentioned a little bit on the previous slides. When you have a battery that's been used, so we know for like about the first 20 to 30% during the capacity loss of the battery, we can predict quite well how a battery behaves through different types of physics-based modeling tools. When the battery reaches 70 to 80%, it becomes much more difficult to predict the capacity loss in the batteries. And so if you go into a sudden loss of energy in a battery, then you're stuck with a non-functioning battery. So it's a lot less reliable when you get to a certain stage of a battery state of health. And of course, also end-of-life batteries, they can be damaged, and there's this, when you collect them, transporting, this is a phase that's also quite high risk. Batteries are considered dangerous goods, so they need to be treated as that. So transport costs for used batteries in particular are very high. And storage can also be a challenge of used batteries in that regards. The last one that we have actually also looked a lot at in a different project here in Norway is the battery room design, which is one of the challenges that we've run into, which was mentioned a bit by Aksel as well. Currently, there's a lot of both international and at least Norwegian standards related to how to install a battery towards the electrical system. But there's absolutely no standards, best practices, or recommendations when it comes to how to construct a battery room when you want to put this battery into a building. Nothing on ventilation, construction materials, fire extinguishing, size of the room, access location, and so on. So this is something that we need to get in place to make things more safe and more standardized. You can go to the next. So based on these challenges that we have identified, there are some solutions and recommendations. As mentioned, the battery regulation will enforce the battery passport starting in 2027. So all batteries larger than 2 kilowatt hours will have a mandatory battery passport. Typical information contained here is the chemical composition, technical specifications, production history, carbon footprint, raw materials origin, supply chain due diligence, social and environmental risk indicators, including also human rights metrics, and instructions for recycling stakeholders to ensure safe and secure handling and recycling procedures. So this will hopefully help in some of the challenges that we have identified. You can go next. We hope also that the battery passport can help us when it comes to the circular economy to make reuse easier access to historical data, and a more transparent value chain so that we can both increase the degree of second life use, but also degree of recycling, and the costs will hopefully decrease. Traceability and stricter requirements for documentation will also make it more difficult to promote and sell batteries with a high environmental footprint. You can go to the next. So for safety, I think as already mentioned, this is a bit of a summary. We need better standards and best practices. We need standards for risk assessment of batteries, design of battery rooms, how to handle a thermal event, both during and after the event, and also training of end users and operators of BESS is a quite important aspect to know how to use it properly. So more knowledge is needed on many levels to make this more safe. You can go to the next. Yeah, I think I have talked quite a lot about this eco-design, so I may not say a whole lot more about this, but to be set more strict rules for eco-design of batteries, clear guidelines for responsibility for collection, and also facilitate more collaboration between industry stakeholders and end users and researchers to share information and knowledge of how we can reuse batteries and accelerate this uptake of second life batteries. And maybe one point that I want to also stress, and that's the incentives. We know that especially the Chinese, they have dumped prices on batteries in the past couple of years. So new batteries have become so cheap that it's really hard to make good economy out of second life, because the batteries that were produced, let's say 3-4 years ago, 5-6 years ago, are much more expensive than the new ones that are being produced at the moment. So in a phase where before we see a bigger growth of the second life market, incentives from governments could be a way to accelerate this forward. How these incentives should be sort of manifested, that could be, I think there's a number of different solutions for that, but some kind of incentives that, or subsidies that will accelerate this process. All right, next I think is the summary slide. Yeah, so battery market, it's still changing quite rapidly, both in terms of technology, design, regulation, market. We see a really fast increasing demand for batteries. We need more standardization and pack design. Repurposing is time consuming, complicated. Hopefully battery passport will help. And we also see that battery system installation best practices are not well established, especially for battery rooms. Those are my key takeaways. So hopefully now we're within time. Sorry, I feel like I was speed talking here.
Yeah, that was really interesting, and we're very ideally in time. So thank you very much, Fride. Yes, we still have time for questions too, and there are a few in the chat. So yeah, about the challenge 7, what tests can be done to allay fears raised in challenge 7? I don't know, should I go maybe back to...
Yeah, what was the number 7?
Yeah, let's go to that.
Yeah.
Right.
Yeah, the public perception. Well, I think there's a lot of testing being done, and we've in this Norwegian funded project that we have done a lot of fire testing on batteries actually, and also extinguishing testing to see how this best can be handled. But I think it's more the fact that at least in Norway we see if there's a battery fire, it gets a lot of attention. We know that there's a lot more gasoline fueled cars that catch fire than EVs, but they don't get the same attention. So I think it also has a lot to do with how it's handled in the media, not so much necessarily the actual facts, but how these are handled. And that's something that we just need to work on, I think.
Yeah. Okay, and then so who is the initial pilot? Aimed at commercial buildings, small and medium-sized enterprises. So I think maybe the question is with not about TREASoURcE pilots as such, but maybe maybe the initial pilot, if some country would like to pilot this solution, what would be maybe the first step, or yeah, commercial building or some other things?
I think it's suitable for at least at the moment, like not the really big batteries, like let's say the megawatt hour batteries, but maybe we have a building in Trondheim where I live, which is a school building for high school kids, and they have a battery of about 450-500 kilowatt hours, which is based on Second Life. It's installed by ECOSTOR. So I would say municipal buildings, public buildings would be suitable, I think. But also small and medium-sized enterprises. It is an advantage if you do have solar cells. or if you have specific needs that, let's say Rudskogen, the motorsport center, which have really high peak loads that can be alleviated using these systems. So I think it's just depends very much on your electricity user profile, because it's not, as you will also see from the results that will be coming from this project, it's not necessarily all buildings that can benefit from a battery. That depends very much on the user profile, the electricity prices, and how you utilize the battery.
Yes, thank you very much, Fride. There's also a message about this was very interesting from one of our participants. Yes, but if you have other questions to Fride, then feel free to write into the chat.
Mm-hmm.
And yes, we'll move forward then to Latvia. So, Egija, are you here?
Yes, I'm here.
Yes. Hello. Thank you very much for being here. And yes, we actually met during an interview with our Latvian colleague and asked to share experience. So I don't know, would you like to share some slides or?
Yes.
Yeah.
Yes.
Okay.
I'll share some slides.
Great.
So that
Thank you very much for
easier.
being here.
All right, I can start, yeah?
Yes, I can see your slides. I don't know, Noman, maybe you can also check if that's fine from your side.
Yeah, it's fine.
Okay. Yes.
Everybody
Thank
sees
you.
it. Yeah, so I'm representing a company called ENGYcell from Latvia, which is multi-asset, multi-market energy management and trading platform. But I'll actually start with a small, intro of where do we come from and why, we actually also met, and how did we get to this point is back in the day, which is like what already, I think 2 years ago, we started by building manufacturing battery energy storage systems on our own. On the right-hand side, you can see, I'm putting in a battery in a container, and that was a container with, used EV batteries. So we were, putting them together from used Tesla batteries, and creating this storage system. Now I have to say, of course, in a way less efficient because it takes a lot of space, but at the same time it has way less power and capacity than you have standard original battery energy storage systems. Then more on the left hand side you see battery cells. We moved from creating battery storage systems from used car batteries to building them from battery cells that we ordered from China. And on the top, you can see just battery cells already put together, like, in smaller modules. And then in the very middle, you see, our first rack that we built. So it's just, battery cells put together, no fireproof system, nothing. And this is where, things got, I don't know how to say, complicated. But here you can see on the left-hand side, that's how it burns. So we almost, burned down our 700 square meter small manufacturing facility. And it all happened just because, actually 2 of the battery cells were faulty that came already from China. And when, full voltage was applied to them, then literally, just because they were faulty and they were kind of like these, how to say, holes in the batteries, then at one moment after this voltage test, after the full voltage was applied, it was boom. And this is what happened. And then after that, we actually went to China to check how they are, how the big manufacturing facilities are, manufacturing these battery systems and how it all works and happens. There we saw that, you have like almost, small rooms in which they place the same battery rack that you see here in the middle that was burning. They place them in small rooms, and then they apply these tests and they check, whether there will be a fire. And if the fire happens, it's in a small room that is, sealed, and there is no damage to the, to the building. So that was basically our biggest mistake, that we didn't have that room. But as we were, doing it all with our own money, we didn't have that much funding to actually build, a manufacturing facility with all the things that you should have inside. So after this trip, we realized that, China is basically 50 years ahead of us in terms of this battery energy storage system technology, speed, cost, that we understood we will never be able to build these systems faster, cheaper, or better than some of the Chinese manufacturers. Not all of the Chinese manufacturers were good. Many of them we saw as very, bad and risky, where we saw immediately where they might have problems later on, as we already ourselves went through the process. But actually, we found partners with whom we will be working together. We signed agreements that we will become their, like representatives, distributors here in Latvia, but only those that we really, really liked, and we understood, okay, these are really good. And after, returning back, we decided that we will completely focus only on, the software side, which is this multi-asset, multi-market energy management and trading platform. Multi-asset in a sense that we can combine different assets, but the main one, you have to have a battery, and then you may have a CHP, you may have a factory, you may have PVs, you may have anything else, but you have to have a battery, and then we can literally manage it all and also trade. We also built load management, load balancing algorithm for the local DSO in Latvia, also for the fact that so that they would not have to invest a lot of money in rebuilding transformers and also sometimes substations. They could place batteries next to it, and literally our real-time, this load management algorithm would actually help them, manage all the loads. And, the DSO would be able to actually save a lot of money on rebuilding the transformers. So yeah, right now, I guess this is, one of the slides that has, from different pitch sessions that, this whole topic about energy volatility, exploding prices, it's a huge thing globally. It's not something small. It's actually really right now #1 operational risk for factories. Many are closing. Many are, just because they cannot sustain the volatility and also the high prices. So this is, our solution is one way how they can, manage it and become more profitable. So all in all, we fused together this industrial control. So if you have a factory, we will manage the whole, in industrial control. We have AI forecasting for solar, for, the consumption in general, and the whole thing, for example, also the imbalance balances and grid trading. All of that goes into one product. And this is the unique side of it, because usually you get 2 out of all 3. This is just, so to understand how it all really works. So you have a battery, and then it's our virtual power plant that, helps you to use your battery and your energy assets for all the other things. So basically, we are like an infrastructure and also, the energy trader. We will, integrate with your renewable assets. We will participate in grid services like frequency and balancing, ancillary services. We will also participate in spot market trading, and then we will have cross-market strategies where, for example, we will, take energy from the TSO and at the same time sell it on intraday. So we will not move your battery. Your battery will stay basically still, but at the same time, you actually earn money with your asset in this way. In the end, what the customer gets from, incorporating the battery storage system into their, business is you get profit from your energy assets. Is it combined energy assets with the solar, CHP, battery, or just battery? You will get profit. If you do have your own consumption as a factory, you will have lower electricity costs. And also you will have more stable grid and backup power And that is more, crucial for some factories that have very sensitive devices and machines that, for example, react very, very much if the grid suddenly, fluctuates. Then, for example, the machinery can also not work properly. So in this sense, you can also, stable the grid for yourself. These are some results that are usually interesting for people to see what does it really mean. For example, here I have a little bit older presentation, so it's still September, October data. But for example, you can see that in September, 1 megawatt, 2 megawatt hour battery in Latvia had a turnover of 76,000, and 60,000 was net profit. Net profit is derived by we take off the power upkeep costs, the DSO delivery costs, and also, of course, our commission, and then we get, your net profit. So 60,000 was in September. October, we can see it was 42,000 net profit. Then I remember November was something 42,000 as well. December was the lowest. It was around 27,000 because December was unusually warm and we had a lot of, cheap gas acquired. And then again, January was already 51,000. And now February will be better, but it's very fluctuating. So you cannot know what will happen really next month because, all of this profit is because of arbitrage on the spot market and also because of, frequency regulation for the TSO. And you don't know what will happen, in 3 days, in a week, in a month. For those who maybe, have not seen really these, storage systems in real life, then these are some of the examples. So on the top of the images, you see 2 images. Those are cabinets. On the top right, those are 4 cabinets, each 125 kilowatts. In total, it's 500 kilowatts and 2-hour systems. Then top images are the containers, which already are bigger. For example, bottom left, there you can see it's a 2 megawatt, 4 megawatt hour system. It's already a container. Usually they are liquid cooling, but some of the systems are also air cooling as the bottom left. On the right side, you can see an image also of how our system looks for the customer, client-facing dashboard. This is usually what you will see, also from similar these service providers. You will be able to follow through, what is happening with your battery, what is happening with your whole, factory, with all of your assets, how much have you earned, from which markets, is it MFRR, is it AFRR, or some other. For the end, this is actually what people don't think about is critical infrastructure. Even if you place just 0.5 megawatt, which seems it's not much, right, for the whole country. But when, service providers like us, we pool all of these assets into a virtual power plant, then your 0.5 megawatt actually participates in, let's say, 100, 200, 500 megawatt pool. So you become actually a critical infrastructure for the government. That is very important to remember when sometimes people think that, it's, just my 500 kilowatt battery, it doesn't mean much, but it's actually very, very important, to keep the frequency, to have more independence in energy wise. Yeah, that's it from me today. So if you have any questions, feel free to ask. If not, then I hope that you, maybe got to know something new or learn something new. Thank you.
Thank you very much. Yes, I think that was a very interesting perspective. So do we have questions for our Latvian participant? No one? No?
Maybe I can ask, what's the total energy pool or power pool you have at the moment? Is it like 4 megawatt, 6 megawatt? How much is that?
So right now we have 23 megawatts.
Mm-hmm.
And then in April, we will already have, I think, 15 or 20 more. So every month it's becoming bigger and bigger because every month, there are people who have commissioned their battery systems. And on average, the battery system is around 500 to 2 megawatts big. for a regular business owner.
Yeah, okay, thanks.
And I was thinking back to your journey from this repurposing experience in Latvia. Maybe you could also share a few learnings from that, or I understand that was quite a like experience too. You tried to repurpose, right? The second life batteries, but maybe you could name some Latvian conditions or something like from Latvia that disabled you to continue, or that you had to actually take another route.
We stopped just because of the fire.
Okay.
Yeah, we stopped because of the fire. We understood it to build actually a manufacturing facility of this to be profitable. You have to put in so much money that we didn't see that potential for it. It's kind of like no one will buy from us because we will always be more expensive than from China.
Okay.
So we didn't see any real business in it. We already invested several $100,000 and we lost it all on the day that it was got on fire. So yeah, it's more from that fact that we didn't see real business in it, except for more like maybe being green, but we understood no, we will of course not subsidize from our pockets, just this repurposing. So yeah, right now we didn't see like real business, but I know companies still also in Latvia that do build storage systems from car batteries, but not really. They're also not focusing that much on used, but more on new ones.
Okay.
Because with used ones, it is a little bit tricky that when you are putting them together and you have one battery, which is, let's say, 90%, capacity left, and then you have another one, which is 70%, or another one at 98%. So that's why they focus more on, these new or slightly used that, there are sometimes cases. For example, there were recently a case where Mercedes batteries were, up for a sale. They were all good, but just that basically the manufacturing in China, they have stopped. They don't need them anymore, but they are still new. So in a way, they're repurposing them so that they would not be thrown away, but they are new in a way at the same time as well. Yeah.
Yeah. Okay, and then there is one question in the chat. Do you have an end-of-life management plan for the battery systems?
No. So this is, we are the software. We are, the company that does the trading. We don't buy the batteries. So, but of course, at least in Latvia, you have to pay like an environment tax when you are importing those batteries here. And then that is supposed to be that, once they will need to be disposed, there will be someone who will actually, do it for you, right? Who will actually, recycle or whatnot. But right now I see that, when, for example, we had this case where we also paid the tax for the battery cells that we got and they burned down, then every company that is, responsible for recycling, waste management, they all declined. They said they will not come for our battery cells. And then, just because we knew an owner of one of those companies, then kind of like we really begged him that, please take them away from us, right? Where do we put them? So then they took them with, but very unwillingly. So right now I would say, also there is this tax that we pay, and it's not a small tax, but it's actually in a way a little bit, scam, because the tax is being taken, but actually the money is not going actually to, to the companies who would need to invest that money really in, recycling. So that is right now what we see, that the biggest problem is this, this end of life. What will happen when, in 10 years, okay, in 15 years, those battery systems will really, end. But hopefully in 15 years, we will already have solutions for that. It's just maybe now for the Baltics, it's a trend. It's, a year ago started this trend with battery systems. So it's very, very new, industry for us in the Baltics in that sense. But I know that I think it was in Estonia, if I'm not wrong, that there was a company that is working with the recycling the batteries.
Noman, I'm not an expert in that.
I'm not sure. I have
You're
not. I
not
have not
sure,
heard about
yeah.
it. Yeah.
Yeah. Okay. Is there another question? Okay, there are questions coming up. So this one we've taken end of life management plan for the battery systems. What happens with the EPR when there is battery repurposing in the countries in this study? So yeah, I'm not really sure what is meant here. Maybe Noman, you can interpret, or what is this
It's
for?
like the warranty or something like the extended responsibility.
Producer responsibility, yes.
Yeah, producer responsibility. Yeah.
Yeah, but maybe we can take this question during Noman's presentation. So thank you very much, Egija. That was really interesting and a good perspective and new perspective for a webinar. Yes, we'll get back to those questions in the chat, maybe after Noman's presentation, because we will again now dive into some of the challenges in replicability in Estonia. So we've looked into a few of them in Latvia. So thanks for our external presenter. And then we studied a bit those in Estonia, and we will definitely touch upon producer responsibility issues. Okay, Noman, yes, the floor is yours.
Yes, thank you again. So let's talk about the replicability in Estonia. So in this study, we explored the Estonian perspective for the repurposing of EV batteries as a stationary energy storage system and for other applications as well. We wanted to know what are the barriers, opportunity, and policy needs. So we had a discussion and 7 focus groups and individual interviews with different stakeholders were consulted. Egija was also one of them, and then we also had one on-site workshop that was titled EV batteries as an energy storage system that we had last year in April. So there were 10 participants from all over Estonia. So the main, it included the Estonian Rescue Board, the Ministry of Climate of Estonia. There were some energy companies, the Consumer Protection Board, and the producer responsibility organizations as well. So the key questions that we ask were these main questions: that what does erudite EV battery become waste versus product again? So what's the criteria that we can classify that it still remains in the category of a product, or is it still, or it can be considered as a waste? So who is responsible for safety? OEM, repurposer, installer, owner, or operator? I think that was also one of the questions that was asked earlier, like who is the responsible party for this second life EV batteries? What data must be shared? For example, currently we don't have battery passports, but in the future we will have these. So we need the diagnostic if it was carried out on the battery, if there was some incident on the battery, so it needs to be reported. So this data must be there, but currently we don't have access to this data all the time because some of the battery manufacturers, they are not giving access to their battery management system. Then what kind of permits are required for building/fire approval, grid connections, and market participation rules? Then what's the producer responsibility and take-back obligation at the second end of life of the battery? So these are the insights from the Estonian stakeholders. So first and the foremost was that there is a broad support but fragmented readiness, that people would like to use these second life EV batteries and they just don't want to discard them as a waste. If they can be used, so why not that they should be used? But here are some like challenges there. So for example, there was a very big concern from the Estonian Rescue Board, as you can see in the right side, that the electricity is traditionally the #1 cause of fire. And the reason is not the device released by the manufacturer, but the installation and usage. So sometimes, and most of the times, actually, the problem is not about the device, it's about how we are using it and how we are installing it. So here is also some statistics. For example, as per the Estonian Rescue Board, 93 building fires caused by batteries and 18 fire hazards were recorded in Estonia in the last 3 years. In the first 2 months of 2025, an additional 6 fires and 1 fire hazard has been registered. An average of 30 to 40 cases are recorded per year. So the fire safety is like a big concern here, as you can see from all these things. Then the second one is this regulatory and role ambiguity in installation. So which institution should oversee the safety installation and approval processes? Uh, Correct installation is extremely important. Repurposer take responsibility. Repurposing is legally the battery manufacturer. So most of the time, as there is no in between or like a middle party here who is actually a repurposer company, so the role is quite ambiguous, like who is the responsible party. And because of this role ambiguity, sometimes we also had the problem with the insurance companies as well. So as soon as the insurance company hear that, okay, there is a second life battery, they will just put extra premium on the building where it's installed. So you have to pay a lot of money just to get the insurance cover, as there is like this role ambiguity here. So there is an absence of accredited conformity assessment body in Estonia. So there is like not like a body that could give some kind of certification to these batteries, that they can be used, they are quite good to use or they are not. And there is also some inconsistent or unclear classification whether it's a waste or a product, because then different rules apply on them. Because if you are just taking out the battery from the EV, then it can be considered as a waste, but still you're using it for some other application, so then it's a product. So these kind of things need to be clarified here as well. Yes, the next slide, please. So as we are talking earlier, the safety and the responsibility are the central concerns. So these extinguishing lithium batteries fire is quite complicated as compared to the traditional fire suppression. So mostly, as I have seen, or like it's an ideal case that these kind of batteries, when they are installed, they should be installed in a separate room, and they should have a separate ventilation system that should not be connected with the main ventilation system of the building as per se. Because if there is a fire, that's a chemical fire, so it can emit some gases that should not go in the main ventilation system of the building. So it should be kept separately. So that could, of course, as Aksel talked earlier, could increase the cost of the ventilation system for the overall building. And it could also should have some additional fire suppressing mechanism, that how to put these fire in case some battery got burning. So therefore, these clear responsibility chains are needed. And as I told you earlier, the insurance companies evaluate these case by case. So sometimes there could be a very high premium and sometimes they are okay with it. So there is not clarity here. Next slide, please. And of course, we have this problem of data oversight and classification barriers for the second life EV batteries. Access to the data, especially the historical data, is quite important. So then we can see if there is some event with the battery or there were some works carried out on the battery. So it's not available at the moment, but probably in 2027, when the digital passport requirements come into play, then it will be a bit more easier to get this kind of data or all this information. So there must be some national regulations as well on these things, and the battery regulation stipulates that the data should be accessible. However, management system can execute it differently, needs for a consensus here as well. Next slide, please. Thank you. There should be also some education, training, and some insufficient technical infrastructure here as well. So training program skills to upskill local engineers and technicians in battery diagnostics, safety assessment, and especially the repurposing techniques. This is very important. I can also share a quick use case from Pakistan here. I'm from Pakistan, so I have this not the EV battery, but a truck battery in my garage, and it's been there for like more than 15 years. No safety, and it's working fine because like 15 years ago, we had some blackouts because the load of on the grid was quite high. So people just started putting, I think, roughly 2 kilowatt to 4 kilowatt hour truck batteries that are used with the engines just to provide electricity for the engine, not for the mobility of the truck, but just for the engine, as we have a small, I think 12-volt battery, something like 60 watt or 70 watt in our cars as well. So if you consider a very big truck, so the battery capacity is something between 2 to 4 kilowatt or even 5 kilowatt hour in some cases. So people just started putting these batteries in their garages, even in their room, and we don't have that many fire caused by the batteries. And we even have a like a scheme that if you usually the battery life is about 3 or 4 years. Depends again on the usage. So when it's the end of the life, you just take the whole battery and you give it to the battery manufacturer. They will buy it back for like 20% of the amount that they will give you the new battery, and then they will reuse some of the cells that are working in the new battery, and you will get a new battery for 3 4 years, and we will just replace the battery. And still a lot of people are using that. I think like in millions of homes these batteries are still working, but now people have put the solar panels and they are using these batteries in the evening time to just save the cost of electricity. So there the system is working quite well. Even I think some of the batteries could be even indoors. But it's again awareness and like how people are using these skills and these things. So I think if we can show the people that these systems are like fine, they are not that dangerous. Very few incidents of fire are happening. So then I think it will be a big step here. And of course, one of the key aspects is the market. The price advantage should be there currently at as the previous presenters also thought that the price of the newer batteries has decreased significantly in the last few years. So it's not a very business-wise viable thing to buy, I mean, second-hand batteries as compared to the newer batteries. So there should be some kind of like government subsidies or some incentive programs or something like this, that you are providing sustainability and you are supporting kind of like green activity. Of course, the market is limited in Estonia because the low number of used batteries. We still don't have that much EVs as compared to, for example, Norway. The EV penetration is modest. I think it's something between 3 to 5% of the total cars. So it's still not there, but probably in the next few years, the numbers will be increased significantly. Next slide, please. So this is the transferability potential between the Nordic countries and the Estonian needs. So first of all, the battery testing facility. In many Nordic countries, there is a battery testing facility. So in Estonia, there is no battery testing lab that can certify these kind of EV batteries as such. The battery data access is a must. So currently, it's very limited data or no digital traceability available. But these early passport pilots are already there, and I think from the next year, the situation will get much more better. Then the fire safety system, no local validation currently, and it's still unclear. But in the Nordic, there is at least in the pilot sites that we saw, there is like integrated fire suppression and some monitoring system there as well. There is repurposing facility. Currently, Estonia lacks of it, and in the Nordics, there are some repurposing organizations already working there. So then we have grid integration. So in Estonia, at the moment, there is not like that much grid integration of battery storage as a backup there. I think in Latvia, it's even more, as we heard from the last presentation. And in the Nordics also there is this virtual power plant and flexibility market. In Estonia there is a market as well still, but you need to be at least 1 megawatt to participate in these flexibility services, or you need to be part of some aggregator that has the aggregated capacity of more than 1 megawatt, as Egija earlier told that they have something around 23 megawatt capacity of these aggregated facilities there. Then the last one is standard and certification. So there are still no standards of certification. Mostly they are governed by the first-hand battery regulations. So it must be sorted out. Next slide, please. So the business model and economics, I will not speak more about it, as Egija has told you a very good business case, but probably it's for the first-hand batteries. It could be for the second-hand batteries as well. So in all these business models, for example, this peak shaving, self-consumption, virtual power plant, or flexibility reserve services, they can be used for these things. Commercial models, for example, you could start small and then build up a modular structure and increase the capacity like small amount of time. The risk drivers, as we have earlier heard, that uncertain remaining life, that the first 20% life, it's much easier to predict that one. But after that, it becomes very difficult to predict the exact battery life, because the packs are quite different. They could be quite heterogeneous. The warranty and liability could be different. And then, of course, the cost drives, the testing time for the second life battery, then the repackaging, electronic certification. This could all increase the initial cost of the second life EV batteries. Next solution. Next slide, please. So the recommendations that we got from these studies, that we need to develop a national regulatory framework for the second life EV batteries, especially for the second life EV batteries. And we need to develop some kind of a pilot project in Estonia that demonstrate the risk mitigation techniques to show to general people that this kind of solution works. And establish some testing and refurbishment capacity in Estonia, for example, a lab that could be very good. And then we need to improve the general awareness on this topic of producer responsibility and ownership transfer as well. Then we need to adapt and adopt the Nordic and the EU standards that are working there quite nicely. Then we need to educate the installer, inspector, and the emergency services. And then we need to promote cross-border knowledge exchange and consortia between the Nordic and the Baltic countries as well. So I think that would be all at the moment.
Yes, thank you very much, Noman. We have some comments and question in the chat. So one of them is battery as a service business would probably enhance safety aspects because the suppliers or producer would take full responsibility. What do you think about this comment?
Yes, I agree with that one, because currently there is like a little bit ambiguity, like who is the responsible party? Is it the original manufacturer, or is it some company who is installing this battery for the second life? So if we clear this role, then it will be much easier for everybody.
Yeah. And can small battery energy storage systems be a solution for powering heat pumps in single family homes?
Yes, why not? Actually, as I was talking about Pakistan, so we have very hot climate there. So usually sometimes these batteries are used to run this air conditioner. So they could have a load up to, I think, like 2 to 3 kilowatt. So why not for a heat pump as well? It's practically the same thing, I would say.
Okay, anyone else wants to also ask questions? If not, then we're actually a bit ahead of time, but I think that's totally fine. We can all go for early lunch then. But what we wanted also to present is the criteria for transferability, because part of the project is doing with the evaluation of how to transfer such practices to other countries. So Noman, we can maybe present.
Yeah, sure, no problem.
Yeah, this criteria, and then go to a quick this feedback session. Yeah.
Yeah. So actually, one of the key aspects of this project was to find out this transferability criteria from Nordic countries to the Baltic countries, as you can see in this image. So in the Nordic countries, as we heard earlier, there is a quite big market of EVs already there. So that's why they have a lot of second-hand batteries there. There are like second-hand battery even companies there as well. So in the Baltics, the situation is still quite behind. We don't have that much EVs here. So therefore not many EV batteries, and therefore not many business case for the second life EV batteries. But slowly we are getting there. So it's not just copying technology, but also copying the process, rules, and evidence. That's why we wanted to learn from the Nordic experience that how can we improve these things in the Baltics. So the next slide, please. Here is some comparison of an EU framework and the Estonian context. So usually this EU battery regulation of 2023 is the one that governs this battery regulation at the moment. But in Estonian context, there is just a little bit like unclarity that again, like what's a product and what's a waste here. So if you take out the battery from the EV, then it's a waste. But if you're using it for some other application, then it's a product. So that's like just a little bit unclarity here that needs to be clarified. Then, of course, the data access from 2027 February, the passports will be available. So then we have more access to these battery data. Then the safety standards, mostly these IEC developing protocols are there, but these are just like only guidelines in the Estonian context, not mandatory. So probably they need to be enforced, these rules in the spirit as well. So then the producer responsibility, then there was a question about EPR. The European standards clarified it, but in the Estonian context, for the second life, it's a little bit unclear, like who will be this one. Then the certification. So mostly these batteries, they have the CE certification, and in Estonian context, there is not much certification at the moment because there is no accreditation national body at the moment. Next slide. We have talked about these things earlier even as well. So there are some practices that, for example, the testing infrastructure in the Nordics, for example, in Sweden, there is RISE, and in Norway, there is this ECOSTOR. But in the Baltics, there is no accredited lab or ad hoc testing facility at the moment. Fire safety, integrated suppression standards evolving. We had an interview with, I think, one company from Sweden. So they were working on this fire suppression mechanism for these kind of like chemical fires, and they were also suggesting some kind of like equipment to turn off these fires as well. So the market used in the Nordics, there are already established pilots there. There is some great integration as well. But in the Baltics, it's still in the early stage. Then the data access, that will be again improved with the battery passports. Next, yes. Okay, so the first criteria is this regulatory and the institutional fit here. So as I explained earlier, the waste versus product status, it needs to be clear pathway for the end of the waste or the remake of the battery. So for example, if we are using this EV batteries for a second life or some other application, then they are a product. They should be considered as a product. Role and responsibilities, the repurposer versus installer versus operator, and this needs to be clarified, like who is the responsible party here. The permitting readiness, the building and fire safety approvals, grid connection processes, they all need to be approved or regulated in some sort of a way. And then, of course, the market access, the ability to monetize flexibility services, as I explained. In the Estonian perspective, the market access is available, but you need at least 1 megawatt to participate in these kind of services. But in some Nordic countries, for example, I know for sure in Gothenburg, a city in Sweden, if you have 100 kilowatts, so you can participate in flexibility services, so which is quite less as compared to 1 megawatt. So in Estonian perspective, the base entry value is still quite high. Next slide, please. So the second criteria is this technical and safety transfer. So when we have this battery data available, hopefully from the next year with these battery passports, then we have all the information about the history, the chemistry, the use profile and diagnostic access. So then it will be a bit more easier to track the health of the battery. And if we have a testing infrastructure, then we can, of course, test the state of the health of the second-hand battery, the failure analysis capability in a much better way. And the fire response readiness, the rescue boat they have some procedures, they have some trainings, and they have also the need to do some kind of like site requirements for these site installations as well. Then for the grid and ICT integration, we need regular monitoring based on SCADA or some energy management system. And we need also to put some kind of cybersecurity mechanisms in place, especially for these kind of large scale battery systems here as well. For the supply chain, we need qualified integrators, spare part and recycling partners as well. Next slide, please. So here are some key takeaways that in Estonia, we can start with a pilot-ready strategy with some clear defined ownership, start monitoring and control sites. Then we can co-develop the national checklist with the regulators plus rescue board and also the industrial partners on board as well. Then we can invest in the testing and traceability, data, degrading and incident loops here as well. So I think that's all from the slides from my side. So there is one more. So this is the decision matrix, how much it can impact the pilot scale and the commercial scale. For example, the regulatory clarity, it's for the pilot sites, it's on medium level, but on a commercial scale, it's a low level. The testing facility, it's on medium level for both cases. The fire safety readiness, it's for a medium scale on a pilot scale level, and it's on a low scale for a commercial scale. So market revenue, it's medium for a pilot scale and it's low for a commercial scale. The supply chain, it's high for a pilot scale and a medium for a commercial scale here as well. Next slide, please. So this is the roadmap that we need to establish a task force in 2025 or 2026, for example. And then in 27, we need to establish some pilot sites with safety monitoring. And 28 and 29, we should adopt this EU battery passport and certification schemes. And then in the later years, we need to also develop a testing facility in 27, 28, and then 29, 23, 30. We need to scale up this repurposing facility and then include the local market here as well. So this is the roadmap, how we can improve the EV repurposing integration in Estonian market as well. Next slide, please. Okay, so that's all from me finally. Thank you very much. Yeah.
Thank you, Noman. Yeah, I think that echoes quite well with all the previous presentations that we had. So sort of summary of everything. But now I've already posted the link to the feedback form, and we actually would love to have your feedback regarding those criteria that we elaborated. So Noman, do you want to walk us through this these 10 questions?
Yes, actually, if you scan this QR code or if you click on this form, so it will open a Google Docs link. So
do you want me to share this on the screen?
Yeah, I can share my screen.
You will, okay.
Yeah, so this is the Google questionnaire. So there are 10 questions. So could you kindly answer these questions as you see fit? And then I can show you the responses. For example, I have already one response here. So kindly just scan this QR code or click on the link and then we can talk about the responses.
Yeah, I think we need to maybe give our participants some more time, but
Yeah.
meanwhile we can look through those questions. That was maybe my idea to introduce those one by one and see maybe some of our speakers or presenters would like to give an answer. Or what do you think, Noman?
Yes. So the question was about this producer responsibility. So generally, I agree that the first company remains responsible even if there is a repurpose, or does it go to the repurposer? If there is a specific repurposer company that buys these second life EV batteries and then they do some kind of certification testing and then they provide this kind of facility for the second life application, then I think the second company should be the responsible one. But if it's not there, then of course it's the responsibility of the initial company.
Yeah, I think
That's
it's
why,
actually a very important topic, yeah, that we've already started discussing in the chat. And Fride also provided for information from her side. So we were discussing with the Ministry of Climate actually in Estonia. And the information from there is that when the repurposer is placing a battery and doing something with the battery in, so to say, yeah, works with the battery and places it on the market, then legally it is considered to be a producer, as I understood that. And in that respect, the repurposer is responsible. But I understand now this is something that that should be needs a further discussion or further input maybe from other institutions too. So it's a challenging issue. Yeah. Do we have something else in the chat? Yes, thank you all very much for taking part in this webinar. But maybe we will also send this feedback questionnaire via emails. What do you think, Noman? Yeah.
yeah,
And
it would be a good idea. Yeah.
Yeah.
We need to give them some time.
It would be nice to get your feedback, and also you can anyway email me all the time about your any other direct feedback regarding this session. But if we don't have anything else, no hands up. I would like to thank all participants who were part of this conversation. I hope you received valuable input from this webinar. And as I mentioned, the webinar is recorded, so I will send this to all registered participants. And we hope you had some new perspectives, practical ideas that you could take back to your work. And we look forward to continue the conversation in some future events. So thank you very much, everyone.
Yeah, thank you very much, everybody.
Thank you. Thank you to all the speakers.
Yeah.
Yes. Thank you. Bye-bye.
Thank you,
Bye-bye.
everyone.
Have a nice day. Bye-bye.
Bye.